Hello student, myself Nimesh Prabhakar. Welcome to Antenna and Propagation lecture series. In my previous lecture, I discussed about the 2-point source, current with equal magnitude and phase. Now here we start this lecture. In this lecture, we discuss first about the 2-point source with current of equal magnitude but with opposite pole, opposite phase. And second, we discuss about the 2-point source with current of unequal magnitude and with any phase. And last, we discuss about the n-element uniform linear array. So in this lecture, we discuss these three topics. So start with the first one, analysis. Like 2-point source with current of equal magnitude but with opposite phase. So here we discuss about the analysis. Like in the previous lecture, we have take the current equal magnitude and equal phase. But here we take current of equal magnitude but the phase is not same of that element. So like this, the assumption is same. Consider 2-point source separate by the distance d and supply with the current equal in magnitude but opposite phase. So the A1 and A2 is 2-point source and we have give the supply, but the current is the equal magnitude but phase is not same. Total field at the far point P is given by, we know that the ET is equals to E1 plus E2, but here the phase is not same. That's why here I have written the minus E1 plus E2, where the E1 is indicate the far field at a distant point P due to point source A1. Same as in the previous lecture we have discussed, E1 is nothing but the E0 e raised to minus j psi by 2. And E2 is the far field at a distance point P due to source E. Like the E2 is indicate the electric field at the far point P due to the A2, and we can write the E2 is equals to E0 e raised to j psi by 2. So now we put this value E1 and E2 in this equation number 1. So we can write this as a ET is equals to E0 e raised to minus j psi by 2 plus e raised to j psi by 2. So now we rearrange the term in the above equation. So we can write this equation as ET 2j E0 e raised to j psi by 2 minus e raised to j psi by 2 upon 2j. So simply we have divided and multiplied this equation by 2j. By trigonometric identity, we have e raised to minus j theta minus e raised to j theta by 2 is equal to sine theta by 2. So now we use this identity in this equation. So here instead of the theta we have psi by 2. So we can write this equation as j2e0 sine psi by 2. But we know that the phase angle psi is equals to beta d cos phi. So we put the value of the psi in this equation. So we get ET is equals to j2e0 sine beta d cos phi by 2. Now we solve the equation for the maximum direction for this 2-point source with current of equal magnitude but opposite phase. So for that, the total field is maximum when sine beta d cos phi by 2 is maxima, same as in the previous lecture. So the condition for the maximum field is given by sine beta d cos phi by 2 is equals to plus or minus 1. So consider here with the distance between the two element is the lambda by 2 and the beta is equals to 2 pi by lambda. So now we put the value of the beta and d in this equation. So we can write the sine pi by 2 cos pi is equals to plus or minus 1. So now we solve this equation. So like sine is cos in the right hand side. So sine inverse plus or minus 1. So sine inverse plus or minus 1 is nothing but we can write as a plus or minus 2n plus 1 pi by 2. And now we put the n is equals to 0 in this equation. So right hand side term become the pi by 2. So we can write the pi by 2 cos pi maximum is equals to plus or minus pi by 2. Now the pi by 2 is cut, and when we solve this, so we get cos pi maximum is equal to plus or minus 1. So we can write the pi maxima for the point source with the current of equal magnitude but opposite phase is the 0 degree or 180 degree. So the maximum direction at the angle of the 0 degree and 180 degree for the current of equal magnitude but opposite phase. Now we find the second one, the minimum direction. So for the minima, the total field is minima when sine beta d cos pi by 2 is the minima. As the condition for the minima field is given by sine beta d cos pi by 2 is equals to 0. So now we put same like a distance between 2 point source is a lambda by 2 and beta is equals to 2 pi by lambda. So equation becomes sine pi by 2 cos pi is equals to 0. So now we solve. The sine inverse 0 is nothing but the plus or minus n pi, and we put the n equals to 0 in this equation. So we get pi by 2 cos pi minima is equals to 0, and so we get the phi minima is equals to cos inverse 0, and cos inverse 0 when at the phi is equals to 90 degree or 270 degree. So the minimum direction for the current of 2 point source, current of equal magnitude but opposite phase is 90 degree and 270 degree. Now half power point, or we can say that the half power beamwidth point. So the condition for the half power point is given by sine beta d cos pi by 2 is equals to plus or minus 1 upon under root 2, same as previous lecture. So here we consider beta is equals to 2 pi by 2 pi by lambda, and the distance between 2 point source is the lambda by 2. So we put here, so sine pi by 2 cos pi is equals to plus or minus 1 upon under root 2. So sine inverse plus or minus 1 by under root 2. So it's nothing but plus or minus 2n plus 1 pi by 4. So when we solve this equation, here we put the condition for the n equals to 0. So we can write this, the pi by 2 cos pi is equals to plus or minus pi by 4. So this is the pi by 4. So here the pi by 2. So we get in the right hand side is nothing but the 1 by 2. So the half power point for the 2 point source with current of equal magnitude but opposite force is the 60 degree and 120 degree. So the field pattern for the 2 point source with the current of equal magnitude but opposite phase is shown in the figure. So here the maximum direction we can see here, the phi is equals to 0 and the phi is equals to 180 degree. Same as the minimum direction we can see here is when the phi is equals to 90 degree and the phi is equals to 270 degree. And the half power point we can see here the 60 degree and 120 degree. So this is the radiation pattern, or we can say the field pattern for the 2 point source with current of equal magnitude but opposite phase. Now we take the third one condition. So third one condition is the 2 point source with current of unequal magnitude. The magnitude is not same in this condition, and the phase is any, like the current we have given with the any phase. So this is the figure for this. So assume that the 2 point source are separated by distance d and the supply with the current which are different in magnitude and with any phase difference, say alpha. So here the phase difference we have given is the alpha. The source 1 is assumed to be reference for phase, and the amplitude of 1 of this field E1 and E2, which are due to source 1 and source 2 respectively at the distance point P. Let us assume that the E1 is greater than the E2 in the magnitude as shown in the figure vector diagram. Now here we consider this E1 is greater than, that means the electric field or the magnitude is greater than the E2. Total phase difference between the radiation by 2-point source at any point P is given by psi is equals to 2 pi by lambda cos phi. We have this equation 2 pi by lambda cos phi, and here we have given the phase of this is the alpha. So here the equation become the phase angle is equals to 2 pi by lambda cos phi plus alpha, where the alpha is the phase angle. Assume the value of the alpha is vary between the 0 to 180 degree. Then the resultant field at the point P is given by Et is equals to E1 e raised to J0 plus E2 e raised to J psi. So Et become e raised to 0 is nothing but the 1. So we get the E1 plus E2 e raised to J psi by 2. So we get the Et is equals to, now we have taken the E1 is common from this equation. So we can write the E1 1 plus E2 by E1 e raised to J psi. Now let me consider E2 by E1 is nothing but the K we put here. Instead of E2 by E1 is equals to K. So we can write this equation as E1 1 plus K, and instead of e raised to J psi we can write by using the trigonometric equation, or so we can write the e raised to J psi is nothing but a cos psi plus J sin psi. And now we solve this equation, so we get we take the magnitude. So Et is equals to E1 1 plus K cos psi plus JK sin psi. And when we take the magnitude, so we get the Et is equals to E1 under root 1 plus cos K psi square plus K sin psi square. Phase angle between the two fields at the far point P is given by theta is equals to tan inverse K sin by 2 K psi upon 1 plus K cos psi. So this is the phase angle at the point P. Now we discuss about the n element uniform linear array. So now, up to now we have discussed about the 2-point source for the different condition. But here we have taken the n element for the generalized form. So at the higher frequency for the point-to-point communication, it is necessary to have a pattern with single beam radiation. Such highly directive single beam pattern can be obtained by increasing the point source in the arrow from 2 to n. So here we have increased the number of array. An array of n element is said to be linear array if all individual elements are spaced equally along a line. So the array is known as a linear array when the distance or the separation between the two elements is equal throughout in the array. An array is said to be uniform array if the elements in the array are fed with current with equal magnitude and uniform progressive phase shift along the line. So here this is we consider the linear uniform array. That means the distance between the separation is same and the magnitude we have given, like the current we have given with equal magnitude and uniform progressive phase shift in these elements. So the total resultant field at the distance at the point P is, we can write Et is equals to E0 e raised to J0 plus E0 e raised to j psi plus E0 e raised to 2j psi plus up to e raised to ej n minus 1 psi. Same as we can write Et is equals to E1 plus E2. Here we have write the n terms. So now we take the E0 is the common from this equation. So equation become Et is equals to E0 e raised to j0 plus e raised to j psi plus e raised to 2j psi plus e raised to j n minus 1 psi. Here we know psi is equals to 2 pi by lambda cos pi plus alpha. So e raised to j psi Et is equals to E0 e raised to j psi plus e raised to 2j psi plus e raised to 3j psi plus e raised to nj psi. Here we have just multiplied both the side by the e raised to j psi. Now we are subtracting equation number 1 from equation number 2. So we get Et is equals to 1 Et into 1 minus e raised to j psi is equals to E0 1 minus e raised to j psi. So now we rearrange this term. So we get Et is equals to 1 minus e raised to j n psi upon 1 minus e raised to j psi. So we write the Et as now we take e raised to j psi in the common from this equation. So we can write this equation as E0 e raised to j n psi by 2 e raised to minus n psi by 2 minus e raised to j n psi by 2 upon e raised to j psi by 2 e raised to minus j psi by 2 minus e raised to j psi by 2. So according to the trigonometric identity, we can write e raised to minus j theta minus e raised to j theta is nothing but the minus 2j sin theta. So now we use this identity. So the resultant field is given by Et is equals to E0 minus j sin n psi by 2 e raised to j psi by 2 upon minus j2 sin by 2 e raised to j psi by 2. So now we solve this equation. So we get Et is equals to E0 sin n psi by 2 upon sin psi by 2, and this E term we solve. So we can write e raised to j n minus 1 psi by 2. The magnitude for the resultant field we can write as the Et is equals to E0 sin n psi by 2 upon psi by 2. Same as we can write the phase for this resultant field as theta is equals to n minus 1 by 2 psi. And we know that the psi is the phase angle is nothing but the beta d cos phi plus alpha. So we can write the theta is equals to n minus 1 by 2 beta d cos phi plus alpha. So this is the magnitude and a phase for the n element uniform linear array. So in this lecture, first we discuss about the 2-point source with current of the equal magnitude but with opposite phase. Then we discuss about a 2-point source with current of the unequal magnitude with any phase. And last we discuss about the n element uniform linear array. Thank you.